Chapter 9, One-Sample Hypothesis Testing. In this chapter, we will talk about the logic of hypothesis testing, the statistical testing of hypothesis, testing a mean with known population variance, and testing of mean with unknown population variance, and testing a proportion. Hypothesis testing is done in the following steps. First, step 1, we need to state the assumption to be tested, right? And then step 2, we need to specify the decision rules upon which to make a decision. Step 3 is collect data and to test the hypothesis. And step 4 is make decision based on the test result. And step 5 is take action based on the decisions made in step 4. So that's the process of hypothesis testing in statistics. State the hypothesis. Now, how we phrase and say the hypothesis, these are kind of different from our normal everyday saying about things, or what we guess, what we hypothesize, and it's different. It's kind of like a unique statistical way that you have to get familiar with. Hypotheses are a pair of mutually exclusive, collectively exhaustive statements about the world. Mutually exclusive means that the two have no overlap. Right? Collectively exhaustive means that you add two together, and that's all the possible outcomes. So one statement or the other must be true, but they cannot both be true. That we know already, because they're mutually exclusive, and they cannot both be true. Cannot both be happening at the same time. So the pair of hypotheses are HO and H1. HO is a null hypothesis. H1 is the alternative hypothesis. These two statements are hypotheses because the truth is unknown. For example, now is we can say that the null hypothesis is that tomorrow is going to be clear and clear, right? An alternative will be is going to snow tomorrow. It's HO and H1. So because we don't know the outcome, because the result, the truth is unknown until after tomorrow. Okay? In statistical test, the efforts will be made to reject the null hypothesis, reject the null. Right? If the H null or HO is rejected, we would then tentatively conclude that H1 to be the case. And the H null, HO is sometimes called the maintained hypothesis. H1 is called the action alternative because some actions may be required if we reject H null in favor of H1. Can the hypothesis be proved? No, we cannot prove a null hypothesis. We can only fail to reject it. This is kind of like our criminal justice system. We can never really prove someone is innocent. We can only fail to conclude that we can only fail to say and he is guilty. If we cannot prove the person is guilty, we know he is presumed to be innocent. This is kind of like similar to that. So the role of evidence that the null hypothesis is assumed true and the contradiction is sought. It's just like in the criminal justice system where the person is presumed to be innocent until found to be guilty. When we test our hypothesis, we could make mistakes. We could commit errors. There are the two types of errors, the type 1 error and type 2. Type 1 error is rejecting the null hypothesis when it's true. This occurs with the probability of alpha. We use alpha to denote the probability of committing a type 1 error. In type 1, we reject null when it's true. When the hypothesis is true, we really should not reject it, right? Because that's the true case. So if we do reject it, then we'll be making a mistake. We'll be committing a type 1 error, the first type of error. Type 2 error, on the other hand, is that if we fail to reject null hypothesis when it's false. And this occurs with the probability of beta. Basically, if it is false, we should indeed reject null. But if we fail to do so, then it's going to be a mistake. And that error is called type 2 error. In this table here, table 9.1, it summarizes two types of errors here. Let's look at the true situation, right? The true situation could be H null is true or H null is false. If H null is true and we reject null, we're committing type 1 error, as said. And if H null is true, we fail to reject null, that's the right thing to do. That's the correct decision. And on the other hand, if H null is false and we reject null, we made the right decision, right? That's correct. And then if H null is false, but we fail to reject, we'll be committing a type 2 error. I'm using criminal justice in this case as example as well. So again, say what is type 1 error? That is reject null when it is true. Now, what kind of analogy can we find in criminal justice? If the person is indeed innocent and we reject null, we reject the notion that he is innocent, what are we doing? Then we'll be sending the person to jail. So type 1 error is indeed like sending an innocent person to jail. Right? What about type 2 error? Type 2 error is fail to reject null when it is false. When it is false, that means the person is indeed guilty, right? But indeed, if the person is guilty, we should put him in jail. But instead, if we fail to reject null, that means we fail to convict him, we let him walk free. So type 2 error is basically like let criminals go free. And that's not good either, right? So that's type 1 and type 2 errors. Type 1, put the innocent person in jail. Type 2, let criminal go free. A statistical hypothesis is a statement about the value of a population parameter theta. This is theta here. And theta could be the population mean or proportion or anything we want to test. A hypothesis test is a decision between two competing mutually exclusive and collectively exhaustive hypotheses about the value of theta. If you want, for example, you want to test to see if theta equals theta 0, that's the true population parameter, right? And that would be our HO or null hypothesis, because normally that's the case. And the contradiction or alternative H1 is that the theta unequals theta 0. And in this case, we call it a two-sided test. On the other hand, if we want to just test to see if theta is larger than or equal to theta 0, or if alternatively as H1, theta is less than theta 0, we call that left-sided test, right? And if we want to test if HO to be theta less than or equal to theta 0, and H1 to be H1 theta larger than theta 0, that's a right-sided test. Okay? So we could test as a two-sided test, left-sided test, or right-sided test. Okay? How do we distinguish between left-sided test and right-sided test? You can look at this little trick here. You can look at the arrow on H1. In here, H1, the arrow here, less than arrow, is pointing to the left. This is the left-sided test. For H1 here, the arrow is pointing to the right. It's a right-sided test. Okay? So basically, the direction of the test is indicated by H1. This pointing to the right indicates a right-tail test. Right? Extreme outcomes are unlikely if theta has a claimed value of theta 0. this arrow left side, indicating pointing to the left, indicates a left tail test. Right? Extreme outcomes are unlikely if theta has claim value of theta 0. An unequal sign indicates a two-tail test. So the sample outcome due to chance variation should be near the middle if theta has a claim value of theta 0. So this is the left tail test, or left side test, right tail test, right side test, or two tail test. When to use one or two-sided test? A two-sided test, two-sided hypothesis test, that is, the theta I equals theta 0, is used when direction is larger than or smaller than is of no interest to the decision maker. When we don't care if it's less than or larger than, we just want to see if it equals or not. A one-sided hypothesis test is used when the consequences of rejecting null are asymmetric, or when one-tailed distribution is of special importance to the researcher. But keep in mind, the rejection in a two-sided test guarantees rejection in a one-sided test, other things being equal. Okay? So what is the decision rule of hypothesis testing? Basically, a test statistic shows how far the sample estimate is from its expected value in terms of its own standard error. And the decision rule uses a known sampling distribution of the test statistic to establish the critical value that divides the sampling distribution into two regions, acceptance region and rejection region. We will reject null if test statistic lies in the rejection region. And known sampling distribution, the most commonly used one is, as you may guess, is the normal distribution or bell curve we talked about before. Okay? So basically, the decision rule for two-tail test will reject null if the test statistic, right, calculated from the data sample, is less than the left tail critical value, or if test statistic is larger than the right tail critical value. Here it is, right? If your test statistic falls in this region to the left of the left critical value, or if it's larger than the right critical value, then we will reject null. If it falls between these two, then in this area right here, then we do not reject null. Okay? It falls within this region. Okay? And that we know it follows the test statistic, the sample, the nature of things follows a normal distribution. That's why we can use normal distribution test to test the hypothesis. Okay. The decision rule for a left tail test is we'll reject null if test statistics is less than the left tail critical value. That's right here. Right? The whole alpha is here, because we do not care about the right-hand side, the right tail. So reject null if test statistics falls in this region. And if test statistics falls in this region up to here to the positive infinity, we do not reject null. That's for left tail test. Yeah. On the red tail test is the same, very similar. We reject null if test statistic is larger than the red tail critical value, right here. If it's larger than that in this region, we reject null. If it's in this region here, to the left, all the way to negative infinity, we do not reject null. Okay? We'll talk about how to actually calculate to find the test statistic and critical value later. Okay? Now let's revisit our type 1 error here. Yeah. Okay, what is type 1 error? What is alpha? Alpha is the probability of type 1 error. That is the level of significance. That is the probability that the test statistic falls in the rejection region even though H null is true. Because H1 for type 1 error is when H null is true, we reject null. Right? So alpha is a probability here, reject null when it is true. Okay? That is put innocent person in jail. Okay? A type 1 error is sometimes referred to as a false positive. is called false positive. For example, if you choose alpha equals 0.05, that's or 5%, then we expect to commit a type 1 error about 5 times in 100 times. So then 5% of the time, we may be wrong in this case. Okay. Type 1 error in a small alpha is desirable, other things being equal. Because of course we all want to be making less mistake, fewer mistakes, right? So, but the alpha level alpha is something that we can choose by our own. If chosen in advance, common choices for alpha are 0.1, that's 10%, 0.05, that's 5%, 0.025, that's 2.5%. 0.01, that's 1%, and 0.005, that's 0.5%. The alpha risk is the area under the tail of the sampling distribution, as we have seen. In a two-sided test, the alpha risk is split, with half the alpha in each tail, since there are two ways to reject alpha. Each has, half the alpha. Okay? The type 2 error, the probability of that is beta. The beta is the probability of type 2 error. That is the probability that the test statistic falls in the acceptance region, even though H null is false. If H null is false, we should reject it. But if we fail to do that, it falls into the acceptance region, we're committing a type 2 error. So beta or type 2 error, the probability is fail to reject null when it's false. That is also fail to reject null when it's false. That is let criminals walk free. Beta cannot be chosen in advance because it depends on alpha and the sample size. A small beta is desirable, other things being equal. Of course, we do not want too many criminals to walk free. Okay? Small beta is desired. Let's introduce a concept called the power of a test. The power of a test is the probability that a false hypothesis will be rejected. Right? Of course, we want to reject a false hypothesis. So the higher the probability, the higher that likelihood, the larger the power. The power is defined as 1 minus b, and b is a type 1 error. A lower b risk means a higher power. Power is reject null when it's false. That's doing the right thing. That equals 1 minus beta. A larger samples leads to increased power. In a criminal justice incidents example, you can imagine that if a court or judge are very handling a lot of have the chance to see or to rule on many cases. That's a large samples, and then we can assume that the judge can make, the court can make better decisions to be fewer errors, so they have larger powers. Okay. The relationship between alpha and beta. Both the small alpha and small beta are desirable. We want to reduce the probability of committing an error, right? Both errors, alpha and beta, type 1, type 2. But for a given type of test and fixed sample size, there is a trade-off between alpha and beta. That is, you cannot reduce both at the same time. If you reduce one, you have to increase the other. If you reduce the other, you have to increase this one. The larger critical value needed to reduce alpha risk makes it harder to reject H null, thereby increasing beta risk. Right? What do we mean by that? Let's think about the criminal justice as the example here. Right? If we want to reduce alpha, alpha is what? Is the probability of putting innocent person in jail. Now, how do we reduce that? How do we put a less innocent person in jail? So basically, we let put more people not in jail, or let more people to walk free, right? If we let more people to walk free, we are actually, in fact, increase our chance of letting more criminals to walk free as well. If you let more criminals walk free, what does that mean? It means actually we're increasing the beta, or the type 2 error. So by reducing alpha, type 1, we're increasing beta, the type 2. So that's why. Right? So, but both alpha and beta can be reduced simultaneously only by increasing the sample size. We can say that we can imagine this as the court being more experienced in making these decisions. The consequences of type 2 error. Nowadays, companies are increasingly wary of type 2 error, that is, failing to recall a product as soon as sample evidence begins to indicate potential problems. They could care less about type 1 error, that is, put an innocent person in jail, or have, just not let a good product to go into the marketplace. But they are more concerned about type 2 error, that is, let criminals go free, or let the defect product to be in the marketplace. That's going to hurt their reputation, the brand image, and the revenues. Okay. Also, there's a significance versus importance issue. The standard error of most sample estimators approaches 0 as sample size increases. In this case, no matter how small, the theta minus theta 0 will be significant if the sample size is large enough. Right? Therefore, expect significant effects even when the effect is too slight to have any practical importance. Okay. Testing mean. If the population variance is known, then how do we test the mean? The hypothesized mean mu0 that we are testing is a benchmark. The value of mu0 does not come from sample, right? It's from the benchmark, from the population. The test statistics, though, compares the sample mean x bar, right here, with hypothesized mean of mu0. And the difference between x bar and mu0 is divided by the standard error of the mean, denoted by sigma x. So the test statistic in this case is x bar, or z score is x bar, the sample mean, minus is the mu0, the hypothesized mu0, divided by standard deviation over the square root of n, the sample size. That's our test statistics. And then we use this test statistics to compare with the critical values. Okay. So, for example, in this example, we want to see if again, first, what kind of test is this? We want to look at H1, and since mu is larger than 260 millimeters, right? But we know this is a red tail test, so we know this is a graph to use, right? We want to see if the test statistics is in this region, gray region, or that's when we reject null, or in this region, that when we do not reject null. The null is, of course, the mu is less than or equal to 260 millimeters, right? So now this is a test, H0 and H1. Now how do we test it? Then we need to specify the decision rule first. For example, for alpha 0.05, that's most commonly used, that's 95%. And for the red tail area, reject the H0 if z equals 1 is larger than 1.645. That's the critical value of z, right? Otherwise, we do not reject null. If it's larger than 1.645, that means in this region we reject null. We conclude H1 that the diameter is larger than 216 millimeter. If not, we do not reject null. Maintain the null. We keep the null. Okay. For two-tail test, we'll split the risk of type 1 error by putting half alpha in each tail. In this case, if alpha is 0.05, we'll put 0.025 here. The critical value is 1.96. If alpha is here, the critical value is plus 1.96. And if the test statistics falls in this region or this region, we reject null. If it falls between, we fail to reject null. We do not reject null. Okay? That's how we test for this hypothesis. Okay? So step 3, we calculate the test statistic by calculating z-score from mu x bar minus mu 0 divided by sigma and the square root of n. Then we make a decision. If test statistic falls in the rejection region as defined by critical value, we reject null and conclude H1. Okay. Now let's maybe at this stage, some of you may recall something about the confidence interval that we talked about. How is this related to or similar to confidence interval? Actually, a two-tailed hypothesis test at a 5% level of significance is exactly the equivalent to asking whether the 95% confidence interval for the mean includes the hypothesized mean. Exactly the same thing. Basically, we just in the case of a confidence interval, we set our confidence level and we want to know where the mean is going to fall within what confidence interval. In this case of a hypothesis testing, we basically get a given level of significance. We want to see if what chance the 95% confidence interval region contains the true mean. So if a confidence interval includes the hypothesized mean, then we cannot reject null. So they are actually based on the same principle, the normal distribution. Okay. In reality, in the real world, actually, we use more often the p-value approach. The p-value or the probability value is the probability of the sample results of one or more extreme, or one more extreme, assuming that the X null is true. Right? That's the probability of the sample result assuming that HO is true. The p-value can be obtained using Excel's cumulative standard normal function of norm dist z. If you have a z-score, you put norm dist z, you get p-value. The p-value can also be obtained from Appendix C2 of your book. Right? Using the p-value, we will reject null if the p-value is less than or equal to alpha. Let's say alpha is 0.05. If a p-value is 0.02, we reject null. Yeah. And that's normally what is reported in statistical testing in the literature. Okay? Testing a mean with the unknown population variant. We're not going to test you, we're not to cover this part in our test. So you can look at this on your own for your knowledge. That is, but I'm not going to test you on that. Okay, it's not required, but you can study if you want to. Basically, with the student t distribution, the degree of freedom is n-1. The test statistic is t, right? Kind of similar. And then the testing hypothesis is very similar too. You said that for z we use t distribution, and if it falls in the rejection region, we reject null. If not, we do not reject null. Okay, and this is the calculated z-score. Calculated z-score using student t. The calculated z-score will compare that with the critical value of t. Okay, and confidence interval versus hypothesis test, as we said, is similar to what we talked about before. The two-tailed hypothesis test at a 10% level of significance is equivalent to a two-sided test of 90% confidence interval. Right? If the confidence interval does not include the hypothesis mean, then we reject null. Testing proportion, we can do the similar test to conduct hypothesis test with test proportion. Again, this will not be in your test, and you can learn this on your own. Right? We need to know, for testing proportion, we need to know the parameter being tested, the sample statistic, the sampling distribution of sample statistic, and sampling distribution tells us which test statistics to use. A sample proportion P estimates the population proportion of pi. Remember that for a large sample, P can be assumed to follow a normal distribution. If so, the test statistic is Z, just as before. This is P, the number of success over sample size. Okay. If it's larger than n times pi is larger than 5, n times 1 minus pi, 0 is larger than equal to 5, then you can calculate Z. And basically testing proportion is very similar. Just two, you have two tail tests, one left tail test or right tail test. Okay. The critical value is given here for the different tests, and then when we conduct the testing, we calculate the scores, the z-scores, and see if it's in the rejection region or acceptance region, just like before. Okay. And this is the steps in testing a proportion. This is calculating test statistics, and also you can use the p-values just as before. Okay. And this is the calculating p-value for two-tail test and the effect of alpha. That concludes chapter 9, testing hypothesis. We'll continue on analysis of variance in the next chapter.